Hey there, folks. This is Mr. Dickin here. Today we're going to be talking about solving systems of equations, in this case linear equations, using tables and graphs. So we will have ultimately four different methods to solve these. We'll have tables, we'll have graphs, and then we'll also have substitution and elimination, which would be the more algebraic methods to solve. So first, let's get through some vocab. First, we're going to be dealing with a system of equations, and anytime we're talking about a system of equations, that's when you have at least two, there could be more, equations that are kind of grouped together. When we talk about them graphically, it's going to be two or more equations that are graphed on the same coordinate plane or the same graph. And we're going to be dealing with something called linear systems. Linear systems are when we have two or more equations, but they're going to be linear equations. Linear meaning that when graphed, they give us a straight line. There's no exponents, there's no radicals, there's no crazy funky business going on. Straight up x's and y's. Or down the road, when we get into three equations, z's will make an appearance. Act surprised when we get there. When we are solving these and finding solutions, that's going to be the set of values. So right here, when I say set of values, it's almost always going to be one singular point in x comma y coordinate. And that's going to be the point that works for both linear equations. Now it's possible that we might have a special case where maybe we have lines that are parallel that never intersect, or maybe that we have lines that graph one right on top of the other, so they intersect infinitely many times. But most case scenario, it's going to be an x comma y coordinate, and we have to make sure that that x comma y coordinate works for every single equation within that system. Again, today it's only going to be two equations. Down the road, we'll get to three equations that we'll have to check, make sure for. So let us see our first example, shall we? Here I've got a system of equations. You'll notice that the system is denoted right here by a brace on the left-hand side. So that indicates that we have every equation within that brace is going to be kind of working together, graphed on the same coordinate system. I have negative 3x plus 2y equals 8, so that's linear. There's no exponents, there's no radicals, x's and y's aren't in the denominator, there's no funky business. Same thing for the second one, x plus 2y equals negative 8. Now, since these are lines, right, these lines are collections of infinitely many points. So there are infinitely many points on this first equation right here. There are infinitely many points on this second equation right here. But there's potentially one single point, one of these infinity points and one of these infinity points that works for both. And that's going to be where they intersect. So first what I'm going to do is I'm going to graph this system. I'm going to graph both of these lines using a free online graphing tool. Some of you may have heard of it, called Desmos. Now, if you've ever met me before, you're going to know that I am probably the world's biggest Desmos fan. If you've never heard of it, it's free. You can access it on your Chromebook, laptop at home. There's apps for your iPhone, Android, tablets, iPads, whatever you got. And it is absolutely amazing. So you'll see over on the left-hand side, I've typed out my two equations. If I graph this first one, you'll see I have a straight line. Should be no surprise, right? We knew this was a linear equation. I'll do the same thing with the second. So I've got my red and my blue line. Ooh, fancy. So these two have intersected at the point negative 4 comma negative 2. So ultimately, when I graph these, I should get the solution negative 4 comma negative 2. So when we get there, act surprised, right? The problem is a lot of us, especially if we're taking like a quiz or test, we don't have Desmos at our fingertips because we don't have our phones right in front of us. Or at least we shouldn't. So we're going to have to do the quote unquote long way about solving this. So what we're going to have to do is take each of these two equations and rearrange them into slope-intercept form. So we're going to rearrange them into y equals mx plus b form. For this first equation, I just moved the 3x over and then divided everything by 2. The second one, I moved this 1x over, so it's negative on the other side, and again divided everything by 2. Here were my resulting equations. So what I can do from here is I can go to my calculator. If you have a TI-83, it's going to be the exact same button sequence as the TI-84. So don't worry about that if you have an 83. To graph these, I'm going to go to the y equals button right up here. And when I graph equations using the y equals button, my TI-84 needs to have these equations written in slope-intercept form or some sort of format where it's y equals something. So we don't have the capability to graph from standard form. We have to get y by itself. All right, so the first equation, y equals 3 halves x plus 4. Anytime I have a fraction, I'll put those in parentheses. So 3 divided by 2 is going to be 3 halves, times x. The x button is going to be right here next to alpha, plus 4. Cool. And the second equation is going to be negative 1 half. Make sure you're using this button down here for negative. Do not use the minus sign. Those do register as different characters on your TI-84s or 83s. So negative 1 over 2, negative 1 half, x minus 4. Now remember, we've already solved this, right? We know what the answer should be. Negative 4 comma negative 2. Let's take a look at our graph. There's line number 1. There's line number 2. So I can see they intersect right about here, right? But it's not too certain. So what I'm going to do is I'm actually going to go through and have my calculator run a calculation as to where these things intersect. So right above the trace button right here, you'll see there's an option that says calc. I'm going to go into that menu by hitting second and then the trace button to give me those calculations. Now we want to find where these lines intersect. Lo and behold, there's an intersect option. So I'm going to go down to option 5, and it's going to ask me the first curve, and it's going to put the cursor on one of my two graphs, okay, one of my two equations. So it's asking, is this one the first graph you're talking about? Yeah, y1, that was my first equation. I'll hit enter to confirm. Then it's going to bump the cursor down. It's going to say, is this the second graph you wanted me to look at? I'm going to say, yeah, that was the y2. That's what I wanted. Then it's going to ask me to guess. This will come in handy later when there's multiple intersection points, but for right now, we don't really care about that, so I'll enter to skip through it. And it tells me the intersection is negative 4 comma negative 2, which, hey, we already knew that. Another option that we have at our disposal is we could take a look at the table. So if you look at the button graph right above that in blue is table. So I'll hit second and go to table. This will give me an XY chart for both of my graphs, the Y1 and the Y2. And what I'm looking for is where do these y1 and y2s match? And I'm looking, hey, right here at negative 4 comma negative 2. This input of negative 4 gives me the same output on both graphs, and that's going to be the only time that that happens. I could scroll through this list forever. The y1 and y2 values are never going to match again, except for the point negative 4, negative 2. Now let's get into writing systems. So whenever we write systems of equations, we're typically going to have some sort of a word problem prompt that we're going to have to work backwards, set up variables, and then using those variables, we're going to have to build equations and solve said equations. All right, so it says you want to buy a camera. You can tell this is a pretty dated problem because no one's using film cameras anymore. Film camera costs 90 bucks-ish. Each photo is 24 cents. Digital camera costs 124.48. Each photo is 9 cents. After how many photos will the cost be the same, and what will that cost be? General tip for word problems, look at the last 1 or 2 sentences, and that will almost always tell you what your variables should be because that's telling you what you're looking for. So I need to know how many photos, that's going to be one variable, and then what will the cost be? That can be my other variable. So I can establish the variables of x is number of photos, y will be the total cost. Well, let's look at scenario 1. So I've got $89.98 plus 24 cents per picture. $89.98 plus 24 cents per picture. Scenario 2 is going to be awfully similar. Now, these are both written in slope-intercept form. So I could absolutely go through and type these equations into my calculator. So I've got 0.24x, oh, that's not an x, plus 89.98 And then y2 is going to give me 0.09x. You don't need the leading 0 in front of the whole decimal if you don't want. Plus 124.48. Now when I graph these though, you're going to notice I'm not seeing a dang thing, right? These graphs aren't showing up. And that's because my window isn't really zoomed in at the right spot of the graph. My window defaults to -10 and +10 on the x and y axes. And there's a good chance that these things aren't within that range. And I'm just looking at the y-intercepts here. This y-intercept is 90, this y-intercept is 125. So my graph is taking place way, way, way up here. So I need to change my window settings. To do that, I'm going to click Window. Now, I don't know exactly where this thing is going to happen, but I know that my x max is probably going to be more than 10 pictures. So I'm going to over exaggerate here, and I can change this later. I'm going to change the maximum x value to 500. Now, if I take a look at the graph, you'll see my x value now extends way further out. I'm going to do the same thing now to my y-axis. I'm going to change that max to 500 again, and I'm probably overshooting. Who knows? I just want to get to a point that I can see one or both of those lines. And hey, I see both of them, and more importantly, I see that they intersect somewhere. So now I can go through that same process of the calc. Option 5. First curve was y1, yes, enter. Second curve was y2, yep, enter, guess, who cares? And I'm getting my x value of 230, so 230 photos. My cost is going to be $145.18. Now, if that was too much and you'd rather solve this algebraically, they're both set equal to y, so set them equal to each other. And you could absolutely go through it and do it algebraically if that suits your fancy. All right, let us carry on. All right, here we have a scenario in which we're given information about sharks. So we have the Greenland shark that grows at 0.75 centimeters per year, and it starts out at 37 centimeters. So I could make the equation y equals 37 plus 0.75x, or 0.75x plus 37. Same thing over here, I could say y equals 1.5x plus 22, where x is going to be the number of years and y is going to represent these centimeters. And once I have my two equations, I can solve using any method I'd like. So it's going to say if the growth rates stay the same, when would they be the same length? Well, it's going to be when would the y values be the same after how many years? Let's say 20 years old, both of them would be 52 centimeters. And again, we're solving that using either substitution or our graphing calculators. Either one would work. How long would each shark be when it's 25 years old? Well, we would just plug in 25 for x to both equations to get the following results: 55.75 centimeters and 59.5 centimeters. And then part C is saying, why would these growth rates not continue indefinitely, right? These lines, if I graph the lines, would go on forever. But why is that not realistic for the sharks? Well, thankfully, sharks are at some point are going to reach their maximum length. They're not going to grow forever. That would be absolutely terrifying. All right, let's get into classification of systems of equations. One of three things will happen when we graph these systems. They'll either intersect once, you'll have one graph, one line directly on top of the other, or you'll have parallel lines. Now, when we classify these, if they intersect, there's going to be one solution, that one intersection point. If it's one on top of the other, they will have infinitely many, and if they are parallel, they will never intersect, therefore they have no solution. We can tell if these things will be coinciding or parallel by looking at the slopes. If the slopes are the same, it's going to fall into one of these two categories. And then it just comes down to, is the y-intercept same or is it different? Now, if you don't want to graph these, you could always take a look at a system, and then you could rearrange both equations into slope-intercept form. Once you have your equations into slope-intercept form, you could say, okay, I'm seeing the slopes are the same, y-intercepts are different, therefore those are parallel. Or over here, if I rearrange this second equation, I'm seeing slopes are the same, but so is the y-intercept. Therefore, these are coinciding. There are infinitely many lines. So that's how we would do it without using technology.